Good morning. Thank you for coming. Today, I'm going to cover the science of climate change. And then tomorrow, we're going to go into the Arctic, what is called Arctic amplification. Because the Arctic is the one area of the world, and the Antarctic, that not only are affected by climate change, but climate change is affected by the Arctic. And so we'll see that tomorrow. And then finally, on Wednesday, we'll go into actually what's happening in the Arctic as far as the plants and the animals. Now, climate change was first looked at, and actually wasn't looked at. Climate change actually confused Joseph Fourier, one of history's great mathematicians. Now, Fourier is the inventor of the Fourier series, which you certainly don't need to know to understand climate change. But in 1824, Fourier, with pencil and paper, no satellites, no computers, calculated that the Earth's temperature should be 0 degrees. And he thought, but it's not 0 degrees. And he didn't solve that. He didn't solve that at all. And he went to his grave thinking, what is going on here? Then postulated and showed that the greenhouse effect was what caused the temperature to be 59 degrees, where the light that is reflected back out is captured by our atmosphere and causes the Earth to be warmer. Now keep in mind that both of these people calculated this with pencil and paper. They didn't have computers, they did not have satellites, pencil and paper. Science of climate science is not rocket science. Weather is, but actually just showing what is happening to the climate has been known for 100 years and not contested. To show you the main driver of what's going on, in 2011, the world emitted about 35 billion tons of carbon dioxide into the atmosphere. To put that in terms that you and I can understand, that's 2 million pounds of carbon dioxide per second is going into the atmosphere. 2 million pounds a second. If you look at a 1,000 megawatt coal plant, it burns about 1 million pounds of coal per hour. That then translates, because coal is largely carbon, into about 3 million pounds of carbon dioxide per hour. Now, before you get too smug, the utility industry only puts in probably 60 to 70%. Every time that you use a gallon of gas, you put about 20 pounds of CO2 into the atmosphere. But I think an incredibly important thing to remember, it's not the utility industry that's using the product. The utility industry may put it in the air. It's all of us that are using. And efficiency is one of the biggest ways that we can fight climate change, by getting more efficient light bulbs, motors, automobiles, etc. This is a graph that shows on the bottom here, the black, the temperature, and on the top it shows the carbon dioxide concentration in the atmosphere. And you can see that there's a real similarity. Let's look at where we are today. This is where we are today. So you can see that probably something is coming, temperature, because the temperature does follow. Now there have been times that the temperature started up first. And in that case, then it released tremendous amounts of carbon dioxide from decaying minerals, or decaying matter, from methane, etc., into the atmosphere. But you can obviously see the close correlation. This is the best study. It comes from Berkeley. It's called the Berkeley Earth Surface Temperature Study. And Berkeley is actually sort of funny. It was funded by an oil company that was trying, actually, I believe, to disprove climate change. Went back and looked at 39,390 weather stations. And the graph they got, you can see. Now, they took this as the baseline in the 1950 up through 1979 period. And so everything else is it over or under that baseline? You can see from the graph that what has happened is that since about 1980, we have really started up. So again, that's 39,390 stations, and it shows that we have raised about 1 degree since then. That's from Berkeley. Now let's look at the science of climate change. Why? What's happening that causes this? The sun emits radiation, quite obviously, and that radiation falls on the Earth's surface. This graph shows that we have ultraviolet, visible, and infrared light. And this is what the sun radiates here. Now, this isn't the total sun radiation. This is the sun's radiation that is falling on the earth. And it's a bell-shaped curve that's determined by the temperature of the sun. When it comes down through the atmosphere, then some of it is absorbed. Some's reflected, some makes it all the way to the earth. But it is absorbed in the atmosphere by various elements. One of the big things that are compounds that absorbs it is water vapor. And here's carbon dioxide, oxygen, and ozone. The ozone layer protects us from the ultraviolet and absorbs most of it, and so forth. So the sunlight that's coming in pretty well gets through the atmosphere. There is a visible light window in our atmosphere that allows this light to come through pretty much unscathed and get to the earth. Now, the sun heats the earth. The first law of thermodynamics is energy can neither be created nor destroyed. This is just a diagram of a power plant, which is my industry, and we can track energy minutely. We know exactly how much energy is coming into any point, how much is going out, and it never changes. The first law is on fairly sound footing. And anything that has more energy coming in than going out is going to heat up. You look at your house. If you have more energy coming in than going out, it will heat up. Likewise, if more out than coming in, it will cool down. So there is that balance. And the earth is the same. And so the question then is, why isn't the earth heating up? We've got all this energy coming in from the sun, but at the same point, we've got to get rid of it. Well, if you remember back to your science class, there are only three methods of getting rid of heat transfer. Heat transfer, conduction. Conduction is where, for instance, you take a laser pointer and you heat up one end of it, and it will gradually heat the other end. That's conduction. But conduction doesn't work for the earth, because for conduction to work, we'd have to conduct into outer space. There's nothing to conduct to. So conduction is not going to work. The next form of heat transfer is convection. Convection is like when a fan blows air through a room. The air is actually moved. That's not going to work either, because in convection, you don't see large chunks of the Earth's atmosphere suddenly tearing away and carrying heat with it. So convection doesn't work. That only leaves the last method of heat conduction, radiation, to get rid of all of the heat from the Earth. And that is how we get rid of heat. We radiate it away in the form of infrared energy. That's called black body radiation. Every single thing in the universe radiates heat. And when it radiates heat, it's according to a very specific law. It's the Stefan-Boltzmann equation. It too was discovered before 1900. No computers, no satellites. It's a fairly simple law. And it states is the energy that any object radiates. My laser pointer, you, an ice cube even, radiates heat. And the formula is fairly simple. It is the total energy radiated per unit of area, like per square meter, is equal to the Stefan-Boltzmann constant, note that word constant, times temperature to the fourth power. So the higher the temperature, the higher the radiation will be. And when I'm talking temperature here, I'm always talking from absolute zero, not 0 in centigrade, not 0 in Fahrenheit, but 0 in Kelvin or the very, very low. It's about negative 273.16 below in terms of Celsius, or 459 degrees below zero in terms of Fahrenheit. That's absolute zero. And you've got to use that in all of these equations. And so we radiate heat away. Now, here's the way it works. Let's assume that suddenly the sun was dark, and it had been dark for millions of years. It popped on. Suddenly the sun comes on. Well, this is the Earth's temperature. At this point, the Earth is going to be at 0 degrees down here. Earth is at 0. It's not radiating anything away. Energy is coming in. So the Earth will start to come up this curve and heat up. It'll get up into here, and it's just now emitting a little bit of energy because it's not very hot yet. It's just starting to heat up. So let's assume the Earth comes up to here, and it will look and it will say it's now radiating more energy, but we're still, more energy is coming in. This is the total sun's energy of 342 watts per square meter, which is the number. The Earth is radiating this much is coming in, so the Earth will continue to heat up. And it will heat up until it gets up to here. At this point, the Earth's temperature will be enough so that we are radiating out as much as coming in. And the Earth is in balance, and that's the way it's been for millions and millions of years. Sometimes the sun's heat goes up, sometimes it goes down a little, but we keep pretty much in balance. Now, at that point, as I said, 342, everything is fine. Now let's look at what frequency something radiates at. If you are some very, very hot object, for instance, a quasar or a pulsar, something really, really hot, a very hot white star, you're going to regulate gamma rays, X-rays, very high frequency radiation. If you are, for instance, our sun, you're going to radiate visible light away. And if you're cool like the Earth, you're going to radiate infrared. Everything radiates. It's a very simple equation, sigma, Stefan-Boltzmann constant, times temperature to the fourth power. But what you radiate depends upon your temperature. You can radiate everything from very low level infrared up to very, very high level, high energy gamma rays, et cetera, et cetera. And so we radiate infrared. Now, what's this infrared? Well, as utilities, we use infrared all the time. We can take pictures of your house and we can tell, ooh, there's red areas. This is where you're losing heat. We take pictures of substations. We have helicopters fly our transmission lines and take pictures. Infrared is very common. You don't see it. There's infrared permeating this room right now because everything in this room is radiating infrared radiation. But infrared is there. Now, this is a very important picture. It's a picture of a man holding a trash bag. And you say, oh, that's great. This is really good. Well, let's look at the same picture if you look at the picture in infrared. That's the same picture. And there's a couple things that are really important. First off, look at the man. The man, if you look at the scale of radiation, this is a lot of radiation and this is not much. The man himself is warm, is radiating infrared radiation away. Every human being radiates about 2,000 food calories per day of infrared radiation. If you're a civil engineer and you're building a building, especially a large auditorium, you've got to take this into account when you design the heating, ventilation, air conditioning systems. You've got to know what the heat load, what the cooling load, but you've got to add to that 1,000 people. If it's a large auditorium, they're going to be radiating energy away. Now, but the most important thing in this picture is look at the trash bag. The trash bag in the visible spectrum is opaque. Light cannot go through the trash bag. In the infrared spectrum, it's pretty much invisible. Infrared will go right through plastic, goes right through it and isn't even stopped. But an even more important thing for our talk today is what is going on with the man's glasses. Look at the glasses. In the visible spectrum, the glass is transparent. Light can go right through it. But in the infrared spectrum, the infrared cannot go through glass. Glass blocks infrared, and that is really important. That, for instance, is so important that different molecules, in this case plastic and glass, if you look at different frequencies, they will have different reactions. And that's all around us. Color is the best example. Different objects reflect different colors to give them the colors that we see. Now, if you don't believe that different molecules have different reactions to different colors, you also don't believe in color, greenhouses, microwave ovens, and a host of other things, which all work on the principle that different molecules react differently to different frequencies. The greenhouse effect takes advantage of that. If you look at a greenhouse, the normal greenhouse like you find in any nursery, what happens is the visible light coming from the sun goes through the glass, just like the man's glasses. Visible light goes through. It then goes to the bottom of the greenhouse and it hits a plant or it hits the floor or hits some object, heats it up, and that object re-radiates infrared radiation. But the infrared radiation cannot get out of the glass. We saw that with the man's glasses. Therefore, the greenhouse becomes hot. That is actually where we get the name the greenhouse effect, and it's the whole principle that we'll talk about today with the Earth's atmosphere. Now, the radiation that is going back out, as we pointed out, is infrared. And so this is the sun's radiation coming in. It's mainly in the visible spectrum. There has to be an equal amount of radiation going out. The area under this curve equals the area under this curve. The two must be equal. But the infrared that's going out is a different frequency. And so it faces a different gauntlet, if you will, of molecules. The molecules are the same, but just like the man's glasses and the plastic bag, they have a different reaction to the infrared radiation that is leaving the atmosphere, and they absorb a lot of it. You can see here carbon dioxide, water vapor is a huge greenhouse gas, methane, etc. And so of the total infrared that is leaving our atmosphere, only this much of it, the blue area here, actually makes it out the first time. The rest of it is absorbed by the various gases. And this is what Arrhenius predicted and showed in 1896 when he first realized that it was this greenhouse effect that is keeping the Earth warm. Now, in that respect, greenhouse gases are good. These are pictures of Antarctica. If it weren't for the greenhouse effect, we would be at 0 degrees and the whole Earth would look like that. Instead, we are at about 59 degrees. That's the total average temperature of the Earth year-round. It's obviously colder in the winter and warmer in the summer, but that's where we are. And so this is what Fourier did not know when he first predicted in 1824 that the Earth would be 0 degrees. It wasn't discovered till 1896, but that's over 110 years ago. It's been known. Now, if you don't believe this and you aren't good at math and don't want to do sigma times t to the fourth and figure out what the balance has to be, go to the moon. Probably a lot harder, but if you go to the moon, you will find out that the surface of the moon is about 0 degrees. The moon is the same distance from the sun as the Earth is. So you'd think it would be the same temperature, but it's not. The moon is 0, we're 59, because our atmosphere acts like a blanket and keeps that heat from escaping just like it does in a greenhouse. Now, you think, okay, we're trapping extra heat. We put more carbon dioxide in the atmosphere, less can get out, we're trapping heat. But if we can get rid of that heat, then we're fine. And the Earth won't heat up. It's like a house. If you are in your room and you turn the furnace on and open the windows in the winter, it might actually get cooler, even though the furnace is going full blast. It's the balance. And so let's look at what's going to happen in this balance. We've said earlier that coming in is 342 watts per square meter. Going out is 342 watts per square meter. And that happens and everything's fine, but actually it's not 342 because roughly here, the blue arrow, about 107 is reflected away. That's why we call the Earth the blue planet. We're mainly absorbing the red and yellow, a lot of the blue, through what's called Rayleigh scattering is reflected away. And so the real number that we need to look at is about 235 that actually needs to go out because we're already reflecting 107. So here we are. We've got 235 in and 235 out because some of it is reflected away. And at that point, what's going to happen if we put a blanket? We'll put carbon dioxide in the atmosphere, and that carbon dioxide will absorb and reflect some heat back to the Earth. And so we're going to reflect back, in this case, about 80. Well, that only leaves us 155 going out. We're out of balance now. We have 235 coming in, but we only have 155 going out. And so the Earth has got to start warming up. But again, can we get rid of it? Well, that's where the rub comes in. If you look at the Earth, we have energy coming in, and remember what we said. We have conduction, convection, and radiation. Convection doesn't work. Conduction doesn't work. Radiation is all we've got. We've got to radiate. We've got to get rid of more energy. But how do we do it? Well, remember the Stefan-Boltzmann equation. The energy that's radiated is sigma times T to the fourth. Sigma is a constant. It's pretty well established that 4 is a constant. The only variable in the equation is T. To radiate more energy, we have no choice. Temperature must go up. And so it's not a question of, is the Earth possibly going to get warmer? It must get warmer. If we're capturing more heat, we're out of balance. The Earth is now absorbing more than it is emitting. The only way we can emit more is for temperature to go up, and that is the basis of the greenhouse effect. Now, let's look at where we are, back to our 235, and we've got to emit more. If we're going to emit more, then we must go up to a new higher temperature. We have T1 here, and that's the emission. If we want to emit it up to 235, if we want to go from 155 to 235, we must go up to a new and higher temperature. The better the blanket, the hotter it's going to be. And the more blanket we put in, the more carbon dioxide we put in the atmosphere, the bigger this disparity comes, and the more that we have to have temperature go up to compensate for the disparity. This is a diagram of the actual heat balance of the Earth. And we have this incoming solar radiation. It's reflected by the surface, reflected by clouds, and it's mainly blue going out. That's why it's called the blue planet. And that's about the 107 that we talked about. And at that point then, with the heat balance, that's the Earth going out there. So let's look at what's happening. 168 is absorbed by the surface. Now if you come over here and look, when the Earth radiates away, it's actually 390. You think, we'll get to that in a minute, how it got there. Only a little bit of it actually escapes. The rest of it, the infrared, is captured by the greenhouse gases and clouds. The greenhouse gases and clouds turn around and they re-radiate more infrared. Some of it goes up, 165, but some of it comes back down. And so in that case, the black body infrared radiation coming down to the Earth is 324. And so if you look at the total energy coming into the Earth here, it's the 168 plus the 324. If you look at going out, it's thermals, evaporation, because it takes a lot of heat to evaporate things. And then it's the surface radiation. Those are equal. So then if you look at the energy out, it's the 107 plus the 235 up here. It all does balance. But as you can see, as we put more greenhouse gases in, less of this will get away. We're going to put more greenhouse gases in, we will absorb more light going out, and the Earth will be out of balance. And the most important thing to remember out of all of this is the only way we can get rid of that imbalance is to cause the temperature to go up, because that's the only way we have of getting rid of heat. Now, this is a graph that comes from NASA. And NASA put satellites up in 1971, so they measured the energy that's being given off, and so it's 100%. They're saying this is what we're giving off. And then this is the wavelength here, and it shows where different things absorb energy. For instance, this is where carbon dioxide would absorb energy. This is where methane would absorb energy. Then NASA looked, and again in 1996, and that's what the graph looked like. And you can see that there are gaps. That energy, we're no longer radiating the same amount of energy. If you look here where carbon dioxide is, we're capturing energy, not as much as going out. Likewise where methane is. Now, if it's not being radiated, we know it can't be created nor destroyed. Where is it going? The only place it can go is heating up the oceans, the atmosphere, the ice, etc. Vice President Gore wrote a book called An Inconvenient Truth. I would say to people that do not believe in climate science that this is an inconvenient graph because you've got to explain where that energy is going. It's not going into space. NASA can measure that. It's rather easy to do. This is a quote from the NASA website, and they are looking at the outgoing infrared radiation. And I'm going to read it to you because it says, decades of measurements from satellites and similar instruments have revealed that Earth's energy balance budget is not in balance. Earth is receiving more energy than it is sending back into space. And that's from NASA. Thus means that the planet must heat up, and in fact already is heating up to regain the balance. And that comes from the NASA website. The last time I looked, it's still on there. Now, if you then look, other people have said, well, we're going to stay on the ground. We're not going up in a satellite, but we're going to look up, and we're going to measure the infrared energy that's coming down from the clouds. Because if they're capturing more, then in order to emit more energy, the Earth has to heat up, and the clouds will be emitting more energy. And what they found out is that the infrared energy coming down from the clouds here, this area right in here, has actually increased by about 2.2 watts per meter squared per decade. When you look at this, you realize that most scientists believe that the difference that threw us into the last ice age was about 1 watt per meter squared. And yet we're changing at 2.2 watts per meter squared per decade. An enormous change for the Earth. So that's the long wave radiation that's coming down to the Earth. Scientists have calculated the amount of extra energy. If you look at all of this down here from this little graph of how much energy is not going into space between 1971 and now, and it's equal to about 13 Hiroshima bombs every second. 13 Hiroshima bombs a second is the extra energy that is being trapped by the Earth's atmosphere. Now, CO2 concentrations have gone up. This is called a Keeling chart. It's from Dr. Keeling. It started it as at Mauna Loa, Hawaii, which he figured was about, the best place to get it. It's not going to have any local fluctuations from plants or anything, so it's on top of Mauna Loa. And the Keeling chart, when you look at it, shows an interesting thing in that every year the Keeling chart goes up a little bit and then it comes down a little bit. It goes up a little bit and comes down. And that's due to the fact, if you really look at the Earth, that you'll find out that most of the land mass is in the northern hemisphere. There's not a lot of land down here, and of course what is down here in Antarctica doesn't grow a lot of plants. And so every summer when the northern hemisphere is growing trees and the leaves are out, the CO2 actually goes down. But in the winter, when the northern hemisphere loses its leaves, it goes back up. And that's why you see the constant little up and down motion in the Keeling chart. If you look, this is a graph from NASA, or a chart or whatever, that shows what has happened to CO2 concentrations in the last few years. And you can see that it did go up. Now, if you still don't believe in climate change, you've got two tasks that you have to explain. One, why does the greenhouse effect, which was discovered in 1896, why does it cease working at 59 degrees? The difference between Fourier and Arrhenius goes up to 59 degrees. Why does it just stop there? The next is, we know that it's warming. The Berkeley Earth surface temperature, thousands of other measurements have said it's warming. So what unknown science, if you don't want to say the greenhouse effect, which the predictions occur and just concur exactly with the what's happening, if you don't believe in that, then what unknown effect that nobody can figure out is causing it? Now, a lot of people have said it's a natural cycle. We clearly have natural cycles. We have natural flying machines also. They're called birds. Does that mean we can't have anthropogenic or man-made flying machines? We have natural lakes. This is a lake in New Hampshire. Does that mean that we can't have natural or man-made lakes? No. So clearly there are cycles that affect temperature that are not anthropogenic or man-made. There's other factors, El Nino, La Nina, volcanoes, and natural solar cycles. And we know a great deal about these cycles. In fact, it is these cycles that give us a lot of the knowledge of what will change when climate forcing changes. Forcing is the energy coming in from the sun and how it impacts the atmosphere. What is the external force to drive temperature? And so the study of these cycles has given us a great deal of knowledge. Now, a lot of people look at, El Nino, and El Nino has driven a lot of the variability in climate. In fact, you'll hear a lot of people say, climate change stopped in 1998. It's got cooler since then, and they're correct. However, that was a huge El Nino year, and you can barely see it on this graph, but 98 and it goes down. But look at the rest of the graph. If you look at the rest of the graph, you'll see, and it won't be another year or so until we break that record. I'm confident in that. We almost broke it last year. In the United States, we did break it. We were up a full degree last year, but worldwide, we didn't quite top that. Energy can neither be created nor destroyed. It's got to be going somewhere. And what we've actually found out in the last 3 years, because of things like El Nino and what's called the interdecadal Pacific Oscillation, is that much of the extra heat is going into the ocean. These are graphs here that shows, this is from Australia, that shows a study they did that shows just this little sliver of heat has been going into the atmosphere and the land, and ocean heating has been a major problem. The graph up at the top also shows temperature and ocean heat content, and you'll notice that there's been periods of low heat absorption, which means that the land or the atmosphere and land are getting a lot, and periods of high heat absorption. The whole atmosphere, ice, land ecosystem is incredibly complex, and it varies. We can't begin to calculate exactly what's going to happen, but the heat has got to go somewhere. So in fact, for the last 10 years or so, we have had a fairly flat period of warming in the atmosphere, but the heat has to go somewhere. It has been going into melting ice and melting oceans. Now, the other main cycles that we worry about are the so-called Milankovitch cycles. Mr. Milankovitch was a Serbian in about the time of World War I. He was actually in prison, I believe, and he started thinking about this and developed these cycles. And they have to do with the Earth's orbit around the sun. The Earth's orbit around the sun is not circular, it's elliptical, and it changes over time. So it will go from one phase to another, and the distance changes. Likewise, the Earth is tilted at 23.5 degrees, but it's not always tilted that way. That angle of tilt will change. That happens every 40,000 years or so. And then the Earth wobbles like a top every 26,000 years. All of these cycles together increase and decrease the solar forcing to the Earth. And these cycles, however, cannot explain the current warming. We know what these cycles are. We measure, NASA can measure incredibly accurately, and the European Space Agency and everybody else, the Chinese, can measure incredibly accurately what is happening to the sun's output. And that output change simply cannot explain what is happening on the Earth. One of the things is that if that was in fact happening, you would find the other planets were also changing. So this is a graph here on the right of the actual solar irradiance, the forcing, and you'll notice it's been going down lately. The Earth's temperature should be cooling, especially it's going up. And this is a graph of total solar irradiance, and here's temperature. This is going down, this is going up. And so again, if it was the sun's output, we should expect to see all of the planets changing. Jim Hansen, who's one of the main chief climate scientists in the world, he's the head of the climate science at NASA, has looked. And if you look at a bell-shaped curve, you'll find that what we call standard deviations. One standard deviation is about the area in between here, and 2 is here, and 3 gets way down here. We call them sigma. And a 3 sigma event should only occur about 2.67% of the time. And what Hansen found was that if you look way back in the 1951 through 1980 period, the Earth's heat, we only had 1 sigma or 3 sigma events about 1% of the time. Today, we're covering 3 sigma temperature events 10% of the time. The Earth is definitely getting warmer. This is the ratio of hot to cold records. High temperature records versus low temperature records. And you'll see for 2012, they were 14-1. In the total of 2011, you can see through here, you don't see any upside down bars. We're having more and more high temperature records and low temperature records. Now, you can't say that any given event is due to climate change. Even something big like Katrina or Sandy, you simply can't say, aha, that is due to climate change. But what we can say with great certainty is that if there were no climate change, we would have some things going one way and some things going another way. We'd have hot records, cold records. We'd have strong storms, we'd have weaker storms. We would have droughts, we'd have rain, we would have different types of weather. But we can say that if you look at the predictions of climate change, everything that is happening, the stronger storms, the droughts, the floods, the increasing temperature, the decrease in polar ice, is all happening in the way predicted by climate change. And weather prediction is an inexact science. We can't predict the weather a month out. We never have and probably never will be able to because of what is called the science of chaos, the mathematics behind chaos, which is a branch of mathematics. You can go to college and take a whole course in it. But what weather people do is they know that they don't know the exact temperature in Tucson. They don't know the exact temperature in Moscow. And so they'll put in the weather forecast like 80.1, 80.2, 80.0 degrees, because they know it's somewhere, they get the 80, but they're not for sure. And they'll run hundreds of models. And the models will come out that, wow, 20% of the time it's going to rain. That's where you get the 20% chance of rain. And so it's interesting, but some of the folks at NASA and some other places went back and they took the exact temperature and pressure starting conditions for the last couple years. And on January 1, if the temperature in Tucson was 80, they put in 80. If it was in Moscow, it was negative whatever, they put in negative whatever. And they ran them forward, but they put in one change. And that one change was they put in today's atmosphere versus the atmosphere that existed 20 or so years ago. And what they found out was that the heat wave and the drought in Texas, when they ran the models, was 20 times more likely to occur with today's atmosphere than the atmosphere that we used to have. The British heat wave was 62 times as likely to occur than if you ran the atmosphere from quite a few years ago. And so it's very clear that we are increasing the probability of these events. You cannot say that any given event is due to climate change. We can't tell what happens to weather right now. We can't tell what caused any individual cloud to form or any storm. It's such a huge complex system that mathematically it's impossible to tell. But what we can say is that all of these type of events are more likely to happen because of climate change. We can easily predict that. And it's sort of analogous to baseball players. Barry Bonds got into some trouble for steroids. You can't say that any given Barry Bonds home run was due to taking steroids. He might have hit it anyway. But what you can say is he was hitting the ball longer and that therefore there were more home runs. And that's analogous to climate change. We can't point to any one event and say that it's due to climate change, but we can say that the events are becoming more frequent and more severe. So climate change has actually already caused the fall of several civilizations. You look in Arizona where I live at Mesa Verde, the Indians 100,000 years ago had to leave. The dinosaurs, when it got cold, when the comet hit, they all died. And even way, way, way back in Earth's history, at that time it was almost entirely CO2, and little microorganisms started producing oxygen and produced enough oxygen to allow animals to live. And my theory is if those little organisms can do it, we can do it. Now, who cares? What difference does a 3 to 5 degree temperature change make? I don't particularly care whether it's 70 or 73 or 74. But if you look at what happens, if you shift that curve just a little bit, you shift the curve and you look at the very extremes out here, and this is where we get all of our strong weather. What you'll find out is you have increased those times and temperatures where you're going to get very strong weather by sometimes 30 and 40%. Another thing that's not subject to controversy, because we can measure this, because of climate change, there's a law that says as the temperature goes up, the amount of water vapor that we can hold in the atmosphere goes up. We can measure that, and it's exactly in prediction with the law. We now have about 4% more water vapor in our atmosphere than we did in 1750, 1850. There wasn't a lot of change, and then it started up. It takes 540 calories per gram to heat and vaporize water. And so when that water is in a storm and it condenses, then it gives that heat back off. And that's what drives stronger hurricanes, stronger thunderstorms, stronger tornadoes, is that extra heat of vaporization. And you look at this and you say, does that sound familiar? Well, if you live in the United States, you look at Katrina, you look at Sandy, we're having tornadoes in January. We're not supposed to have tornadoes in January, and we're constantly shattering the $1 billion mark. If you want to find someone that really believes in climate change, go to the insurance companies, talk to them. So we're having more intense hurricanes, and probably about the same number of hurricanes, the meteorologists believe, but they're going to be more intense. If temperatures and storm intensity were the only problems with climate change, we'd still probably say, well, we can live through that. It's not good, but you know, it'll be all right. It's not worth it fixing it. But that's not the major effect of climate change. The major effect of climate change is the change in weather patterns. And what we're finding there is we're going to have huge droughts, and I mean large droughts. If you look at the major weather patterns in the world, we have three main cells. We have the polar cell, where air sinks when it gets cold and comes down and goes back up. The Hadley cell is the one we really want to talk about. In the Hadley cell, the warm, moist air is here. Now remember, weather is nature's way of redistributing energy. We get a lot of energy down here at the poles. We don't get much up here or down here. So we got to redistribute this energy. And so as this air evaporates here, as the water condenses, then the air will be hot when it loses that moisture from condensation, and it goes up and it comes back down. It comes back down at about 30 degrees latitude, south and north. And that's why we find a lot of deserts there. That hot, dry air that lost its moisture on the way up is coming down. The Sahara Desert, the Gobi Desert, the Southwest US, et cetera, et cetera. What the studies show is that as we get more climate change, we get more energy, and the Hadley cell is going to move slightly north, and that will move the desertification area northwards. And in that case, we are going to have huge droughts. Jim Hansen, the chief scientist at NASA, who I previously mentioned, has given numerous talks where he says the southern US will become uninhabitable by 2100. It will look like the Sahara Desert. If you think they've had water problems in Atlanta in places, just wait. This is not some environmental group. This is the National Center for Atmospheric Research. This is the US government's National Center for Atmospheric Research. You can find the same thing from the Europeans, whoever you want to look at. This is a drought index. And temporarily in the Dust Bowl, it hit -3. By the end of the century, we think it could go -8 to -10, and much of the Mediterranean could fall to 10 to 15. This is what it is projected to look like by the end of the century. Italy, southern France, you can kiss the wine crops goodbye unless you're going to irrigate them heavily. That's what we're facing. There's a tremendous drought. The US has gone through a drought this year that was worse than the Dust Bowl now. We've had a lot of irrigation and things. But what do we do when those aquifers run dry and we have no more irrigation? It's not be the first time that we have reached what we call a tipping point, where climate radically changes. You can find hippopotamus fossils and hippopotamus bones from just 50, 60,000 years ago beneath the Sahara Desert. It used to be warm and wet down there. Sea level rise is a major problem, not only because it will flood places, like this woman lives in a little island in Panama, but as we raise the sea level, imagine what Sandy would have been like, the flooding, if the sea level would have been 2 feet higher. It would have inundated much more of Manhattan and New Jersey. Then many nations, the US and Europe will probably survive, but many of these nations literally will not survive. The Maldives are gone. Their highest point, I believe, is 6 or 7 feet above sea level. And so that is the science of climate change. Now tomorrow we're going to go into a lecture, which will be much shorter, that talks about what is called Arctic amplification. And then the next day we'll look at actually what's happening in the Arctic. Thank you.